Hi students, I'll try in this educational video to technologically introduce the principal rules that permit to size a tank's reinforcement plate based on the French calculation code CODAP, of course, as simply and as clearly as possible. Okay, let's go. Well, first, as I said in the previous videos, when we perform an opening on a tank's shell or a tank's forward head, the stress around this opening is amplified by 3. This may cause a resistance problem in the neighborhood of the opening. In order to avoid this resistance problem, we have to increase locally the thickness in the neighborhood of the opening. This is technologically carried out by installing or welding a reinforcement plate around this opening. This is the technological interest of the reinforcement plate. It's to note also that this reinforcement plate will have some specific dimensions, which are the thickness of the reinforcement plate and the width of the reinforcement plate. And in this educational video, I will try to explain how to correctly size the thickness and the width of the reinforcement plate. Of course, based on the French calculation code CODAP. Now the figure that you see depicts how the reinforcement plate highlighted here in red is installed around the nozzle carried out on an opening, obviously. And the figure or the picture at the right is a real picture which indicates how the reinforcement plate is welded on the shell, and it's around an opening, and on this opening we have a nozzle neck and a flange. And the picture at the bottom depicts isolated reinforcement plate which normally will be installed around opening carried out on tanks. Well, now it's important to note that the sizing of the reinforcement plate is based on the model that you see now in the slide. Of course, this model is extracted from the calculation code CODAP. So, this model depicts a shell with an internal radius Ri and a thickness T. And we have an opening, and on this opening, a nozzle is installed. The nozzle have an internal diameter D subscript NZ to say the diameter of the nozzle, the internal diameter of the nozzle, and the thickness of the nozzle TNZ. This nozzle may have an exceeding inside the shell. This exceeding have a thickness T prime NZ and a length L prime NZ. It's to note also that this nozzle have also a length normally L subscript NZ, which is the length of the nozzle outside the shell. And you can notice on this model that we have a portion of the shell characterized by its cross-section S. This portion will participate in the resistance around the opening. And we have another portion of the nozzle characterized by its cross-section S subscript NZ to say S nozzle, and also this portion of the nozzle will participate in the resistance around the opening. And we have the reinforcement plate that we will install around the opening, and this reinforcement plate is characterized by its cross-section SR. For the portion of the shell which will participate in the resistance of the opening, we have the dimension capital L to characterize this portion of the shell, and for the portion of the nozzle participating in the resistance around the opening, it's characterized also by its length outside the shell, small l, and a length in the exceeding inside the shell called L prime. The model depicts also that the opening creates a certain cross-section G within the shell and also within the nozzle. It's to note also that this nozzle may have an exceeding equal to 0, so there are no exceeding within the shell. So at this case, we will note that the dimension L prime and Z will be equal to 0. Now, based on this model, CODAP states that this characteristic dimension capital L, which is related to the portion of the shell participating on the resistance around the opening, this dimension capital L is equal to a certain factor K0 multiplied by the square root of the mean diameter of the shell multiplied by the useful thickness of the shell. And this factor K0 can be obtained from this chart, which indicate that when the factor delta, which is the internal diameter of the nozzle D and Z divided by the square root of the mean diameter multiplied by the thickness, is from 0 to 4, K0 is equal to 1, but from 4 to 16, the K0 is obtained as 13 by 12 minus the factor delta divided by 48. And here, CODAP states also that the length of the portion of the nozzle participating on the resistance around the opening. So we have two characteristic dimension, L and L prime, capital small l and small l prime, and they are obtained by the formula that you see in the slide. Here, small gm means the mean diameter of the nozzle, T and Z means the thickness of the nozzle, and L and Z means the length of the nozzle, and I explained how to obtain this length in the previous video. And of course, D prime M is the mean diameter of the exceeding of the nozzle, and T prime and Z is the thickness of the exceeding of the nozzle. Now, always based on this model, only when the diameter of the opening small d is higher than 0.14 multiplied by the square root of the mean diameter of the shell multiplied by the useful thickness of the shell, only in this case we need a resistance verification. And this resistance verification is stated by CODAP using the inequation that you see now in this slide. We can easily deduce from this inequation that the cross-section SR of the reinforcement plate, which is obviously equal to the width of the reinforcement plate multiplied by the thickness of the reinforcement plate, should be higher than all this quantity. So when we set a value for the thickness of the reinforcement plate TR, we can obtain the minimum value of the width WR of the reinforcement plate. It's important to note here that usually the thickness of the reinforcement plate should not exceed 1.5 times the useful thickness of the shell or of the formed head if the nozzle is carried out on a formed head. Well, it's all for this educational video. Please don't hesitate to mention all your remarks and suggestions in the comments. Thank you very much.